looking to have a discussion about axioms. In particular, we want to answer that first question that we posed at the end of the last video, which is what makes for a good set of axioms. We got to figure out which axiom sets should be allowed and which ones should not be. So I guess we should take it basically as we have this idea of an axiom, but we really haven't defined an axiom system because we haven't figured out what's allowed and what's not allowed. So in terms of what a mathematician wants with a good axiom system, is there's sort of an optimization problem to deal with here. On the one hand, we want to assume as few things as possible, obviously, right? I mean, you don't want to assume too much. That would be insane. You're trying to prove things. You're not trying to discover truth, not just assume it. The whole point was to prove things. So we want to assume as few things as possible. But on the other hand, we want to be able to prove as much as possible. I'm going to be working on the assumption that our proof rules are good enough. We haven't dealt with the second problem yet, but we will in the next video. I decided as I was going through these that I kind of needed to do this one first, although those three questions that needed to be addressed sort of mingle with each other. It's kind of hard to pick the order to do them in. But I'm going to work on the assumption that we've kind of dealt with that second problem and kind of shown or justified that our proof system is adequate. In other words, the proof system is doing the best it can. Now we got to make sure the axiom system does the best it can. So on the other hand, we want to be able to prove as much as possible, and that is that the responsibility of that at this point in the context of this video has fallen to the axioms, not the proofs. So that's the optimization problem. We want to assume as few things as possible. We also want to be able to prove as much as possible. Pretty simple. So some kind of balance here has to be struck. So let's start with like kind of the most obvious thing that won't work, and kind of just to kind of look at it and figure out why. So suppose we simply said anything goes. Suppose any set of sentences could be taken as an axiom, as a set of axioms, as an axiom system, I should say. Then everything would be trivially fully axiomatizable because you could simply take my axiom system to be every true thing in the natural numbers, and that would be stupid. That would be absurd. There's no, that defeats the whole purpose, right? The whole purpose is to discover truth. So if I just took every true thing as an axiom, if I allowed every set of axioms, then I could just take all the true things as axioms, and then I'd be done. So that shouldn't be allowed. And maybe in a more kind of more importantly than that's kind of defeating the purpose, maybe, is the fact that the other thing is, like, I can't look at this set of axioms. If I said that this was the set of axioms, then I have no idea how to write that set of axioms down, and that also kind of won't do. Axioms should be things that I should be able to write down and have a full list of them, right? So that's not going to do for that reason also. At the very least, an axiom system should be a set of sentences that I can write down. And this is not something that I can write down because I don't know what it is. So that won't do for those two reasons. So let's kind of look at the next naive question, which is like, let's go extreme in the other direction. What if we said that axiom sets had to be finite? You're not allowed to have infinite sets of axioms. That makes sense given what I just said, right? What I just said is that we want to be able to write them all down. So, if it's not finite, then how am I able to kind of fully express them? So that's, let's look at some key axioms. So what I want to do to address kind of both of these questions is I want to look at a couple of example axiom systems and just kind of use them to think about this. Now, the things I'm about to show you will look very scary. They're sets of axioms that are complicated. These are real axiom systems. So, but we're only looking at them to get a sense of the kind of what an axiom system is, not to understand the axioms inside of the thing. So don't worry too much about what you're about to see. Meanwhile, here's this. So these are the axioms for Peano arithmetic. So the Peano arithmetic axioms are pretty much like an example of a good axiom set for the natural numbers. A lot of mathematicians will tell you that these are, these kind of are the axioms for number theory that most people have settled on. The standard model of the natural numbers is assumed or does satisfy all of these, and we generally do assume that the natural numbers satisfy all these properties. And we can kind of go through them all. So, but we don't have to really. But this list looks pretty finite, right? I mean, I wrote infinitely many here, but ignore that for a second. This list looks fairly finite. I don't think I want to go through each one. This one just says that For all x, if you take the successor, you're not going to have 0. That's obvious. If you have, for all x and for all y, if the two successors are the same, if x plus 1 equals y plus 1, then x equals y, sure. Then these are axioms for like the less than. So if x is less than its successor, then x is less than or equal to the thing before the predecessor, right? Obviously, for all x, there's no x is less than 0, sure. These are pretty self-explanatory for the most part here. So here's another one for less than. This is transitivity. So I think this is so if x is less than y. So either x is less than y, or x is equal to y, or y is equal to x. One of these three things has to be true, sure. It's not transitivity, but x plus 0 equals x. There's the additive identity. These really aren't that hard to understand. And let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's this last one. If you've ever taken like a discrete math class or something, then you're very familiar with induction. And these induction axioms, so you'll know then, are pretty important. And there's more than one of them. We're basically saying that there exists an axiom. Don't worry about what this really says. I'm not even going to get into what it says. But what it's really saying here is that there exists an axiom for every formula. So for any well-formed formula which has a single free variable, I have an axiom. So that's why there's infinitely many here. These are all single axioms, one at a time. This is a single axiom, this is a single axiom, this is a single axiom. They're all single axioms, but then this is actually an infinite set of axioms. And so if you take them all together, the entire set, you generally denote it F equals the Peano axioms. This is an infinite set. And so if this is an infinite set, and in order to have induction as an axiom, you need an infinite set, which it seems like you do because you need to be able to kind of use any formula here, then this assumption that we had before about axiom sets must be finite is a little too constrictive, I think. Let's see another example of that. Let's move down again. These are the axioms for kind of like the simplest version of set theory. So, you've got ZFC set theory, which involves this other axiom called choice, which I didn't include here because I didn't care. And then also there's this axiom of foundation, which tends to not need to be there, but I kind of think it does, but I didn't include it anyway because, again, I just kind of wanted to make a point. And again, here's a single axiom, here's a single axiom, here's a single axiom. I don't care what these are. Here's a single axiom. And then here's one that's not a single axiom. This is an infinite set of axioms. For each form, they all serve one purpose, but there's infinitely many of them. We're saying that for every formula phi, in which I is not free, something is true about it. So again, this is an infinite set of axioms, one for every single formula. Same thing down here. For every formula in which something else is not free, we have this, right? So again, infinitely many. Infinitely many. And so, these are two important, very important, axiom sets. Neither of them are finite. But we also can't just say any of them do. So what do we do? Well, let's think about this. Well, here's the thing. This is an infinite set, right? But nonetheless, I wrote it all right here. Same thing down here. This is an infinite set, but I put it all in this box. So there is something finite about both of these axiom systems. But it isn't that the sets themselves are finite. What is it? It's not that the sets are finite, it's that the sets are finitely describable. Remember that? That's what we need. An axiom set, a valid axiom set, a good axiom set, doesn't need to be finite, but it does need to be finitely describable. I do need to be able to write them all down on paper, in the sense that I should be able to write something down on paper from which you can extract the full list in a mechanical way. Finitely describable. That's the property we were looking for. That's the good property. That's what it really means to be an axiom set. And I think that makes perfect sense. I think nobody should have an issue with that. So that's the conclusion. So what axiom sets should be allowed? The finitely describable ones. The ones such that I can write down something like this on paper, wherein you could extract, if you wanted to, every single one of them. You know, in an infinite list. You could. There is an algorithm that makes it go forever. Do you see what I'm going with this? The finitely describable ones, i.e., what am I going to say? The computably enumerable ones. So we are once again confronted with computability. I cannot write. I.e., the computably enumerable ones. So from now on, I am going to assume that all axiom systems are computably enumerable sets. So let me write that down. So that's going to be kind of retroactively built into the definition. So definition, an axiom system is any computably enumerable set of sentences. It must be computably enumerable. Why? Because what we really are saying here with computably enumerable is finitely describable. What we're really saying here is that it needs to be able to be written down something like this. This is finite describability. Look, all of them are here. And so we know now that remember I said earlier, we kind of made sure to be very comfortable with this fact that finitely describable means computably enumerable. Computably enumerable means finitely describable. We talked a lot about this, and this was one of the reasons why. And another thing I should probably say at this point is that you're probably getting the sense now that computability theory doesn't just factor into the metamath in one way. It's just seeping through the walls everywhere. This is all. There's no one sense in which computability theory plays into this. It's every sense. We can't get away from it. They're practically the same field. They're practically the same theory. There's practically no separating them, in my opinion. So anyway, that's a big result. We needed that. We needed that connection. We needed to make sure that we understood that there's a built-in computably enumerable aspect to any axiom system, in the sense that all axiom systems must be computably enumerable to be regarded as valid. That's the defining feature of all of them. So with that said,